I was talking about the Mobius assignment. Those announcements will be posted online. I'm going to just continue right where I was because that's going to be the first words of the new recording, right? So there's going to be about 10 questions on the assignment. It's going to pull from an option of about 10 questions per question. The questions will be randomized in order. You will not be able to go back. So you won't be able to return to a question once you've done it. You have the question, you answer, you move to the next one. You're going to have 48 hours to complete the assignment. There is no time period other than that within there, so you can take all 48 hours to do it if you like. You can do it in 10 minutes. It's entirely up to you. Don't leave it till the end. Just because of the way that Mobius works with scheduling things, it's going to start at midnight on like 12:01 a.m. on a Thursday, and it will go till midnight on Friday night. I recommend you do not start the assignment at 11:50 on Friday night. That seems like a bad idea because it won't allow you to submit it if you leave it till after midnight. You don't need to do it all in one sitting. Yeah, I think I think that's what I want to say about that. So there will be a practice one next Friday, and then the first real one will be the Friday after. We'll do one couple weeks apart there, 1 week apart, and then it's gonna be every 3 weeks or so for the final two. So there's yes, today is Friday, so a week from now it's the practice. You can still get benefit from it, but it can't hurt you. So it's all upside. I would just even if you really don't want benefit from it and you decide to like randomly type in numbers or letters or whatever the entry happens to be for a given question, still go through the process to make sure that you can see how to submit it, how to access it, so you're not going to be surprised when the real thing hits. Because the last thing you need is more stressors because of the way the system works. Okay. Good. So I'm going to move on with the course material. And where we were talking about last class, we got to this slide here, examples with pi bonds. And I said, okay, we're not, I think we finished up the slide before it. Oh, mouse is on the wrong screen. Mouse is on the right screen. No, it's not. Where the hell's my mouse? There's my mouse. Now it should be on that screen. There it is. Okay, so we finished off here. And I want to just go through a few examples with pi bonds to talk about how to organize these. Now, we've already seen a lot of this stuff. I'm not going to redraw these. ChemWare does have, like the Mobius interaction does have some good interactive images and videos and things that work. I'm not sure how interactive they are. They're images, they're videos. I'm looking at these kinds of bonds. What I want to talk now is about a sample with a lone pair. And so here, what we were talking about was that these lone pairs on oxygen were sitting in sp2 orbitals. And that's because we could get lower in energy if we had them in an sp2 orbital than if we left them in a p orbital. So this is, this is one of these linear combination of atomic orbitals drawings. So if you're a really good drawer, that's like a perfect answer, except if I asked you to label the bonds, you would have to go in and label the bonds. We can have a few others that we're going to think about. I'm going to bring in another example on the next page. So we're just going to go through 3 examples and we're going to move on to the next subject. So if we're looking at carbon dioxide, so this question is basically saying label the hybridization geometry and bond angles around each atom other than hydrogen, provide an LCAO. So we'll have to do one of those drawings. I could just say provide an LCAO and it would still get us the right spot. So what we have to do, the first thing we got to do is we got to figure out the Lewis structure of these things. If you don't know the Lewis structure, you have nowhere to start. So with CO2, You don't need to draw the Lewis structure. I'm not asking for the Lewis structure, but not a bad idea if you're not quite sure where to start. That is not CO2. That's what you draw when you're not paying attention. Okay. Now we need to figure out the hybridization of all the atoms present there. And so what we're looking at then is, I'm going to say count the number of things around each of the atoms. And that is a good guess on where to start with the hybridization. We'll figure out the caveat I'm adding to that. So on the carbon, there are two things. There is an oxygen and another oxygen. It needs it is sp hybridized. It's making 2 sigma bonds and 2 pi bonds. The oxygens each have 3 things. This oxygen has a carbon, and it has a lone pair, and it has another lone pair. So my best first guess at this is it's sp2. And this, of course, is a symmetrical molecule, and this one's sp2 as well. Perfect. Right, Amla. The carbon is sp, oxygens are sp2. Now we need to draw that. So what I would recommend when you're drawing is draw your center atom. And now you know it's sp, so the 2 sp orbitals need to be perpendicular to each other. Now they're each going to have that little other lobe on the other side of the atom. We're going to not draw that. I'm okay with you not drawing it because it's going to make your design messy. Because remember, an sp orbital looks like that. Makes LCAO messy. So I'm okay with you leaving those off. So I got a question, why are the oxygen sp2? You know what, how about we draw it out and maybe that can answer it a little bit better. So I said count the number of things on it, and I agree with you that that sounds a bit like trust me, and trust me is not a good policy. Well, it is, but I don't like that as an answer. So we're going to draw the sigma bond to the 2 oxygens. They're each going to need a sigma bond. Now, this carbon is going to then have 2 p orbitals on it. And the p orbitals are going to be, yeah, lone pairs do count for hybridization, that is right. And doesn't it have to do with the oxygen being trigonoplanar? Why is the oxygen trigonoplanar? We're kind of getting a little bit, it's trigonoplanar because it's sp2, and it's sp2 because it's trigonoplanar, and we're getting into a bit of tautology. And so we'll come back to that question in a second. And so it's going to have a second p orbital, which is perpendicular, coming in and out of the page. Now, each of those p orbitals is going to interact with one of the oxygens. So I'm going to arbitrarily decide that this oxygen here is going to be lined up in the plane with that. And that means this oxygen's p orbital must be lined up with the other p orbital into and out of the plane. Now we're almost done, except we haven't, we've got 4 orbitals on carbon, right? We've got, where's my mouse? We've got P, we've got P, we've got an sp, and we have an sp. So we have the 4 orbitals on carbon. Our oxygen has an sp and a p, and an sp and a p. So our oxygens only have 2 orbitals. They need 2 more. And there's things we could do. So one thing is the oxygens could have another p orbital. One of the lone pairs of the oxygens could be sitting in a p orbital. That's high energy. If it's in an sp type of orbital, it's going to be lower energy. Because when you hybridize, you lower the energy. So your choice is to either put electrons in a higher energy state or a lower energy state. You're going to pick that lower energy state every single time. So oxygen chooses to put its lone pairs into sp orbitals, in this case sp2 orbitals. Because sp2 orbitals are lower in energy than p orbitals. So if it can put them in an sp2 orbital, it will. And so what does that look like? Well, they're going to be at 90 degree, at 120 degrees, so this sp2, and I have kind of, and at 100 and at 90 degrees, so this p orbital. So one is going to be in the plane of the page and up that way, and the other one is going to be in the plane of the page and kind of hidden behind this p orbital because that's coming up towards us. So we have a lone pair in there and a lone pair in there, and those are both sp2. And I should put that in blue, but I just can't be bothered to switch the color of my pen. This oxygen is also going to have two sp2 orbitals. Same argument. It could put them in a p orbital, but if they were in a p orbital, they'd be higher in energy than if they were in an sp2 orbital. And atoms are lazy, electrons are lazy. I can't emphasize that enough. And so the geometry of those things, well, I can't put them in the plane because the p orbital is in the plane, and they need to be at 90 degrees to the p orbital. So one of them is coming directly out towards us, kind of, and the other one's going back and away. So it's sort of an interesting feature of this is although CO2 is a linear molecule, we think of it that way, one of those oxygens has its lone pairs kind of up and down in the plane, and one has its lone pairs going back and forwards. So they're kind of at 90 degrees to each other. And it's just, it is that because this is what's required of the geometry. If we go with a slightly long, you know what, this is a stupid example. I'm not going to do it because it's too simple and we're not going to learn anything. So let's do a slightly harder example that I am going to make up on the spot. CH2, CF, CO. Yes, that's a real molecule. Okay, so I've written a molecule there. It is in this whatever writing thingy this is, condensed structural formula. And we want to switch into a line angle formula. Because the first thing we need to do is figure out why is O in brackets? It means the O is not attached to the H. If I had not had the O in brackets, I would write COH, and that would mean an alcohol. But the O in brackets means the O is attached to the carbon and the H is attached to the carbon. So what I'm saying is this is not an alcohol. So the first thing we need to do is draw the structure because there's nothing you can do with that. So I'm going to give everyone, take 10 seconds, try and draw it, and I'll draw it in 10 seconds. Okay. So hopefully you all have beautiful structure line structure diagrams. When I do give that, do try and do it because you can always correct it and then there's no embarrassment. But if you're not practicing, you're in trouble. I'm going to explicitly write out all the atoms in this thing at this point. Make sure we keep track of them. So that's what that means. We have a CH2 on the left, and then we have a carbon. And we note that, hey, that carbon is only attached to 3 things. That means it must have a multiple bond. This carbon is also only attached to 2 things, a fluorine and a carbon. And so it makes sense to have that double bond there. Then this carbon is attached to a fluorine, and this carbon is also attached to a carbon because fluorine can't be attached to two atoms. So we don't read that as C attached to fluorine attached to carbon. We read that as C attached to fluorine, C attached to carbon. And then the brackets mean the oxygen is attached to that carbon, but not to the hydrogen afterwards. Would it be a correct Lewis structure if we drew the carbon chain straight instead of bent? It would be a correct Lewis structure. It would be an incorrect line drawing structure. And your geometry would be wrong. I think it's not a bad idea to try and get the geometry right here because you're going to make your job easier when you try and draw out the linear combination of atomic orbitals. You want to minimize how much stuff you need to do. Okay, so let's consider our lone pairs. So we are going to start by doing this wrong because that's always a good way to start. So we're going to follow the rules that we have seen. The fluorine is attached to the carbon. It's just the fluorine can't be attached to two different carbons. So once again, last time, the oxygen is in brackets to indicate it's not attached to the thing after the bracket. So if I'd written COH, no bracket, that means carbon attached to an oxygen that's attached to a hydrogen. But C bracket OH means carbon attached to an oxygen, carbon attached to a hydrogen. And it's a parenthetical notation, like you can kind of delete it. So if we follow the rules, we just take a look at this, we go, okay, that carbon is attached to three different things, it is sp2. This carbon is attached to three different things, it is sp2. This fluorine is attached to four things, three lone pairs and a carbon, it appears sp3. Because it's got four things. This carbon is attached to three things, it is sp2. This oxygen is attached to three things, it is sp2. And all the hydrogens are just S, because they can't hybridize because they're sad. Okay, so I had the sp3 in brackets, so I'm obviously lying to you. And the reason I'm lying to you is because we have not taken into account resonance. It all comes back to resonance. So, how can we draw, things are atoms and lone pairs. Things that can sit in orbitals. Okay, so how do we draw a resonance structure for this? Well, we've got a few. So we can walk through this, and we're going to spend a lot more time doing this in a couple of classes. And I should draw these effing hydrogens. Okay. So we have that one. I can then draw another resonance structure. And note in these cases how I'm drawing the arrows. I'm showing the flow of the electrons. So in structure one here, I had electrons flow from the double bond onto the oxygen. That gave oxygen extra electrons, so it's O minus. We stole an electron from the carbon, it became positive. I could then remedy that situation by using the double bond between a carbon and a carbon to move two of the electrons and kind of pivot them on the carbon. And so that's allowed. You're either allowed moving electrons from a bond onto the adjacent atom, or you're allowed to pivot them around the adjacent atom. And that's kind of what we're doing here. And so we're forming a new double bond there, leaving that one positive, and the fluorine has disappeared. But there's another one as well, because this is what we've done drawing involving the oxygen. But there's nothing stopping us. I'm going to change color. Where's my cursor? There it is. There's nothing stopping me using that green arrow, which would lead to this odd guy. Is it a good resonance structure? Not really. It's a pretty shitty resonance structure, but it's possible. And then we have one that we haven't drawn and we might not have seen a lot of. You can use the fluorines lone pairs to make another resonance structure. You can move multiple bonds at the same time. Somebody's saying, shouldn't something be positive? No, I think everything that should be positive is positive. That first molecule is completely neutral. So Suhib. And here what I've done with the green one, I moved the electrons from the double bond onto the carbon, so it's got extra electrons. Yeah. You don't, so lith-midge, you don't need to show all the electrons and lone pairs on all the structures, but you should show them if you're using them to move them. And it's not a bad idea to keep track of them because you're going to easily lose track of them. I've guarantee you if you don't draw them in, you will lose track of them, then you'll get confused and it'll all go wrong. Following the good habits here. So in all these cases, I can always check to make sure I've done something reasonable. I posted about this. For example, here I didn't draw any the lone pairs on that oxygen or on this oxygen. And I've left them off the fluorines in a lot of cases. Like this negative charge is a lone pair. If you count the number of electrons, it's all the same in all these molecules. That's really tedious. What you do want to make sure is that your charges are equal. So this is a neutral molecule. It better be neutral all the way through. So my charges always cancel out. Yeah, you do need arrows. Yes, you need arrows on your resonance structure. If I'm asking you to draw resonance structures, I want to see how you got them. I think for the lab, you don't need to, but if it's the exam, definitely. It depends how we can input data, right? Yeah. So what we're saying here is that these are all valid resonance structures. And actually, let's just take a quick look at A and B. I'm just going to call these guys A and B. Which one of those is the more stable resonance structure? Of just A and B. I'm waiting for some of the answers to come in. Okay. Okay, so anyone arguing A? Why are you arguing that A is a more stable resonance structure? Okay, I see the two main arguments right there midway in the chat. So Amla is arguing for A, I hope, and she's saying F is the more electronegative thing. So you don't want to put a positive on an electronegative atom, you want a positive on an electropositive atom. That's true. But I see two responses there saying the octet rule, and that's truer. The octet rule is number one. Things need 8 electrons. And in A, that carbon only has 6 electrons. It is actually missing electrons. They are not there. Whereas in B, the fluorine still has 2 lone pairs. If you count its electrons, it's got 8 around it. It's formally positive, but everybody is obeying the octet rule. And so B is the better resonance structure. Amla is a boy. I'm sorry. Thank you. Resonance structures that involve radicals are very possible. I put them in the announcement because they're possible. Don't worry about them very much for now. We're doing all ionic. Unless there's a radical in the question to begin with, radicals are stupid. And we're going to come back to radicals near the end of the class. So where I'm going with this is when we drew this resonance structure, suddenly we had a resonance structure where that fluorine is making a double bond. And remember, resonance structures are different representations of the same thing. We're using different Lewis dot structures to represent the same molecule at the same instant in time. These aren't flipping back and forwards. They're all true at the same time. So what that tells me is that fluorine must be able to make a double bond. If it's not able to make a double bond, it can't make B. but B is a resonance structure, and resonance structures are good. So what that tells me back here when I'm assigning a hybridization is that cannot be sp2 or sp3, because an sp3 atom cannot make a double bond because it has no p orbitals. So fluorine must be sp2. So atoms with lone pairs want to be as sp3 as possible. So they want to get as close to sp3 as they can, but if can use them for resonance, must have a p orbital. So whenever possible, atoms with lone pairs will be sp3. So normally that fluorine would want to be sp3. That's what those electrons want to be in the lower energy orbital, and sp3 is lower than p. But because the p orbital can do resonance, that's stabilizing. And that's better than having them in a lower energy orbital. Yeah, you would assign sp3, but then you go, oh, look, it can do resonance. It's got to be sp2. And so that's where I'm thinking that's what I'm saying. You always have to be thinking about that. Sorry, I'm going to close this. Actually, give me a second. I am just going to turn off Microsoft Teams because it is just going to be sending in endless. Yes, please keep. Where's my mouse doing? And on here, on my main computer, I also need to deactivate closed Teams. I think there's a way for me to silence Teams, but I've never really figured out how to do it. It kind of overrides everything, like a lot of Microsoft stuff. It just wants you to talk about it. Okay. So yeah, I think that's the main point I want to make on this, is be careful of atoms with lone pairs and things that can make resonance. And you're going like, okay, how do I know that? A good rule of thumb is if a heteroatom, and that's an atom with a lone pair, hetero different, and basically it's any atom that isn't carbon or hydrogen. My handwriting is getting worse. Is next to an sp2 or sp carbon, it can do resonance. You're going to see this whenever you have a fluorine or an oxygen or a nitrogen adjacent to a carbon that's making a double bond, it will be able to do resonance. If the carbon next to it is sp3 and it's only attached to sp3 carbons, it can't do resonance. It's a good rule of thumb, but it's always good to check the resonance structures. Okay, I think that's... I'm not going to bother drawing the LCAO because it will take about 20 minutes. If you're asked to draw the resonance structures, would you draw the green ones? The B is an important resonance structure, A not so much. So I would expect you to probably draw B, but not A. A kind of is, well, A is different from any of the others. Like normally if you have two resonance structures where you can break the double bond and you can put like you wouldn't draw the resonance structures where you broke the first bond that we had, this guy here. I'm pointing at my screen, which really is not very helpful to anybody. And you wouldn't break that so the electrons go into carbon, the carbon would become negative and the oxygen would be positive. You wouldn't draw that resonance structure. It is a resonance structure, but it's directly counteracted by this one here. And this one here is better. And so you would never see that one. But A and B are not counteracted by any of the resonance structures above, so I would actually probably draw them out. Yeah, F is sp2. That is what it is. It is sp2. You will be asked to assign hybridizations. Okay. So one of the things that comes from all the p orbitals and s orbitals is the s orbitals, or sigma bonds and pi bonds, is sigma bonds come because the two sp3 orbitals meet, right? And those can spin. They're symmetrical. Like we have these in 2D, but these are three-dimensional balloon animals, right? And so they can just spin on each other. So single bonds can rotate. But double bonds can't, because in a double bond, you're locked at the top and you're locked at the bottom. And these lobes need to be parallel to each other. And so double bonds cannot rotate. Double bonds are locked. Unless you break the bond, you can't rotate them. So if you try to twist this thing, the more you twist it, it falls out of position. And if you actually twist it by 90 degrees, then there is no bond because there is no overlap. Neither of these lobes do not overlap at all. And so you have absolutely no interaction. So normally this doesn't occur. You need to heat things up a lot to get double bonds to rotate. Okay, Bennett, I bite. Bennett asked, what would the resonance hybrid look like for the previous molecule? I'm going to put it in the top corner here because there's a little bit of space. So every bond that is intact at all times is drawn out. That's all the single bonds plus these hydrogens. All the double bonds are broken at some point, so we're going to dot all the double bonds. You can break all of them. Where's the biggest negative charge density? Well, it's over on this oxygen, definitely. This carbon's got a little bit because of A and B down there. Where's the positive charge density? Well, you can get a little bit of positive charge here. You get a little bit of positive charge on this carbon, on this fluorine. You get a little bit of positive charge on this carbon. This carbon's got negative charge here, negative charge there, positive charge there, and those are going to probably cancel each other out quite a lot. There's not going to be very much negative left over. I don't actually even know which way that lies. I would not give you such an ambiguous molecule where you kind of have things pulling against each other, as I do here. It would be a lot smoother. But I think that would be the resonance hybrid, no overall charge on the molecule. Because it probably doesn't completely cancel it out. It's not a one. It's not a +1 -1. It's probably a. I think there is going to be a very slight partial negative on that charge, if I was going to compute the charge density. But if you wrote a really slight partial positive, I'd also mark it right. And if you wrote no charge on it, I'd also mark that right. It's pretty damn close. Okay. What I want to talk about here, though, is the cis and trans, because I know you guys have seen cis and trans for the cis butene, same side, trans butene, opposite sides. So I almost went into like Latin classical studies instead of, chemistry, because I really liked it. And so I always think of these in terms of European geography. And so what we have is cis means same side for me. That means Cisalpine Gaul, which is the part of France, for the Romans, the part of France which was on the close side of the Alps. We now call it northern Italy, like around Milan and Turin. And so it's on the same side. and it was on the same side of, and you know, the Romans were all very Roman-centric. And so it was on the same side of the Alps as Rome. And so it was on the same side, Gaul, Cisalpine. Trans is Transylvania, so it's on the other side of the forest from Hungary. And so trans across, cis on the same. I'm not exactly sure, Ashita, if I understand your question. The overall charge on the molecule is the overall charge on the molecule. Again, resonance structures are not different things. They're different drawings of the same molecule at the same time. We're just trying to better understand how the electron cloud is organized. Okay, so Vesper theory predicts bond angles in molecules. We've drawn a lot of LCAOs, and we've talked about how we can use those atomic orbitals and combine them to make pseudomolecular orbitals. If you want practice drawing, and I'm sure you do, questions 1.22 to 1.25 are pretty good for that. Okay. Oops. Yes, please keep all the annotations. I'm going to move on to the next lecture, lecture 5. So we'll move through this a lot faster because I think this is going to be a little bit of a break. Bond angles. Bond angles for SP are 180. Bond angles for SP2 are 120. Bond angles for SP3 are 109.5. Yeah, they vary a bit. Yeah, that's an approximation. Who cares? Close enough. You got a tetrahedron, you got a triangle, and you got a straight liney thingy. Okay. That's all I have to say about on Blackboard. Yeah, this is on Blackboard. So we're going to move through this relatively quickly because this is going to be review for a lot of you. But again, just in case, we're going to talk a little bit about constitutional isomers and stereoisomers because we're going to be talking a lot about stereoisomers. We're going to talk about bond polarity again, and we're going to talk about molecular polarity, and then we're going to discuss intermolecular interactions because a lot of chemistry comes from how molecules organize themselves and also driven by intermolecular interactions. So, isomerism. We're going to basically, by the end of a few lectures from now, we're going to have a flow chart with different types of isomers. The highest degree of isomerism is, so an isomer is, anything is an isomer if it has the same molecular formula. It's got all the same atoms in it. A constitutional isomer differs in how the molecules are bound together. So we can have a structural formula C5 or a molecular formula C5H12. There's multiple ways we can draw C5H12. We can draw it in a straight line. Well, a bent line because we're not barbarians here, like people in Cisalpine Gaul. We can draw it as the 1-methylbutane. That is also, or 2-methylbutane. That is also C5H12. We've got neopentane, C5H12. And that's basically what we've got. Yeah, I don't think we have any other options. If we have C5H10, we're down 2 hydrogens. So if we remove 2 hydrogens, that means we've got a double bond somewhere because we got rid of 2 hydrogens. That's C5H10. That's C5H10. One, two, three, four, five. That's C5H10. That's C5H10. You know, you got a bunch that you can draw. Yeah, and we can cyclize it. Yeah, so this is pentene. Or cyclopentane. Because you get the same effect molecularly if you remove 2 hydrogens, make a double bond, or you cyclize it. Because remember, an alkane has a formula CnHn plus 2. And that's because every carbon's got a proton, got a hydrogen, except for the final ones, which each have, every carbon has 2 hydrogens if it's a straight chain, except for the final ones, which have 3 hydrogens, because they're at the end and they're not attached to another carbon. So CnHn plus 2 is the formula for an alkane. So this is a standard alkane. I know it's because 5 times 2 plus 2 is 12. 5 times 2 is 10. So it's supposed to be an alkene, or it could be a cyclic molecule. These are constitutional isomers. They're attached differently. Stereoisomers have the same connectivity, but differ in how the atoms are oriented in space. So we just saw butene. So this is trans, and that's cis. Okay, but we start running into trouble when we get a molecule like that. Yes, you're absolutely right. I am not paying attention to what I am writing. That is cis, and that is trans. Thank you. Yeah, did I write H? Did I just write N? Yeah, I even said 2N. It's been a long week. Okay, because that's not obviously cis or trans. Like the fluorine is cis to this methyl group, but this methyl group is trans to that methyl group. So you're not sure what to call that cis trans. So we're not going to use cis and trans. I know you've been taught it. I am going to use it so rarely because it's pretty useless. Instead, I'm going to use something called E and Z. And so that comes from, I actually don't remember what these mean. There's something in German. It's all in German, and I can never remember what it means. What we're doing here is I want to be able to assign whether this is an E or a Z alkene. And it's clear, because what we're going to do is, there we go, somebody actually knows. What I'm going to do is I'm going to right down the middle of the double bond, I am going to draw a line. Sweet. Then I'm going to draw a second line. That's line number 1. Then I'm going to draw a second line through here. That's line number 2. Okay. Now what I'm going to do is I'm going to change color of pen. And I'm going to look on either side of line number 1. I'm going to try and figure out what is the heavier system. So these are methyl groups. Let's just put those in. I didn't draw these in because we just did a standard drawing and I don't need to put them in. So I'm trying to figure out, is fluorine heavier than methane? And if I ask that question, it's a difficult question to answer because what do I mean? What I mean is which of the atoms directly attached to the carbon is heavier? Which has the higher molecular weight? Fluorine is a higher molecular weight atom than carbon. And so fluorine gets priority. You know what? There's way too many numbers on this slide. I am going to say heavy and light. Now it's all relative. The fluorine is heavier than a methyl group. Or the fluorine is heavier than a carbon. It's not heavier than a methyl group. It's heavier than a carbon. On the other side, the carbon is heavier than a hydrogen because everything is heavier than a hydrogen. Now I've assigned those two. Now I'm going to look at the line number 2, and I'm going to try and, you don't need to draw line number 1 and line number 2, you just need to do this in your head. I'm going to think, are the heavy guys on the same side of that line? And the answer is yes. My fluorine and my carbon are on the same side of that heavy line. And so what that means is they are on the same side. So this is a Z alkene. heavy groups, same side, or cis. The heavy groups are cis to each other. And E is if the heavy groups are heavier trans, or I prefer if they're opposite to each other, because that's kind of like opposite but not. So if somebody has a heavy accent from somewhere, I'm not exactly sure where. Yeah, so ZAME, exactly. So what you're doing is you need to compare the fluorine and the carbon on the same side, like on this carbon, which of the two groups is heavier. And then once you've assigned that, you'll find out for this carbon, which of the two groups is heavier. And then you see are the heavy groups next to each other or across from each other. The heavy groups are next to each other, it's ZAME, it's Z. If the heavy groups are across from each other, it's E or opposite. The other way you can remember this, if that just seems even too lame for you, is let's say you had a double bond like this, and you had a double bond like that. That looks a bit like a Z. That looks a bit like an E. But this is organic chemistry, and it's not allowed to make sense. And so those need to switch. The thing that looks like a Z is an E. The thing that looks like a Z, looks like an E is a Z. So if what they look like, it's the opposite of that. I think they missed a real opportunity here to go with that, like the shape kind of thing, called like C and Z or something, but they didn't do it. So the heavy groups are always, if the heavy groups were here and here, they'd be on opposite sides of this line, and that would make them E because they'd be opposite each other. And it would also look like a Z, and it doesn't need to make sense, and so it would be E. That they're never above and below each other because you're comparing this to that. So this is heavy relative to that. Yeah. So you're always comparing on the same carbon. You're comparing those two, you're comparing those two. And then once you figure out who fought that, it's kind of like, the way I've drawn it, it's almost like a bracket, like a playoff pool. We have the winners of the Western Conference coming out here having a fight. This guy wins. Then he goes against the winner of the Eastern Conference. And they're both on the top side, and then the analogy breaks down. But it's that shape. That's the order of comparing. The two on the left, the two on the right, and then the winner of each of those. My money's on Tampa. Okay. So, one form of stereoisomer is this ZE stereoisomerism, where you have double bond. Everything is connected to the same atoms. They're constitutional isomers. They're not constitutional isomers, I mean. Everything is connected to the same atoms. They are stereoisomers because they're different in how they're arranged in space. And stereo is all about space. Okay, that takes us to 220 more or less, and I think we will pause there and we will get into discussing polarity and intermolecular forces in about 20 minutes next class, and we're going to be moving on. So I'm going to put up the next slideshow as well for Monday. I will see you guys all Monday. Happy E and Zing and playing the nomenclature game. Yeah, I'm uploading. Yeah, I'm uploading all the marked up PowerPoints to Blackboard. So yes, that will absolutely go on there. Yeah, of course I'll update that. That should go up pretty soon. I'm going to put this one up as well, like what I've done to date, and then I'll replace it once we have the final version. And that's what I'm doing. Okay, there's no other questions. I am going to go do something else. In reality, trans and cis isomers exist naturally, like randomly. They exist naturally, but not randomly. E double bonds are almost always more stable than, Z double bonds are almost more, no, see, even I get confused. E double bonds are almost always more stable than Z double bonds because having big groups apart from each other is favorable energetically. So most natural molecules have the big groups apart from each other. Most double bonds in nature exist kind of in a trans configuration. and they do not interconvert. You need to heat them enough to break the pi bond. So we're talking a few hundred degrees Celsius. And at that point, normally most molecules in nature start decomposing when you hit a few hundred degrees Celsius. So that's not really a thing. Atomic size is atomic weight, elemental number, where it is on a periodic table, Mohammed. So Mohammed said, do we judge which molecule is heavier based on atomic size? You judge it based on which one has a higher atomic number. And for those weird ass elements where there's actually a couple of them, right, where I can never remember which ones it is because it's in the part of the periodic table I don't care about. Your atomic weight actually goes down as you increase number of protons. But it's by number of protons in a nucleus. That's what matters and defines how heavy an element is for this naming. And we'll figure out what to do soon when you have the same element there and you have extended chains. Okay. Okay, everyone, have a good day. Thank you. There don't seem to be any more questions, which is good.